Decision trees are the single best place for you to begin your real-world machine learning journey. And here's why. First up, decision trees are state-of-the-art for real-world business data. And what I mean by that is data that comes in a tabular format. So if your data comes in the form of an Excel spreadsheet, or a CSV, or a database table, decision trees are battle-tested and are state-of-the-art for crafting useful machine learning models. And quite frankly, the vast majority of business data comes in a tabular form. So you're good to go. 2, decision trees are as easy to learn as they are powerful. Now, I don't expect you to believe me, which is why I've created this crash course. This crash course is a purely intuitive introduction to decision tree machine learning and will tell you without any math, without any mathematical equations at all, how decision trees learn from data. And this is super important because that allows you to craft the most useful machine learning models. So just so you know, this crash course is designed to be very much akin to my live virtual training as possible. So I'm going to make mistakes. You might hear ambient noise coming in, all that kind of thing. And the idea is to simulate what my students see when I teach them machine learning, like over Zoom, for example. So just bear that in mind as you watch the video. Also, if you'd like to follow along, there is a link down below in the video description where you can get the files for this crash course. So you can get a PDF of the slides, you can get a Jupyter notebook of all the Python code, and you can get CSVs of all the data so that you can replicate everything that you see in this crash course, as well as experiment and play around with the code and with the data and see how your machine learning models change and evolve as you change stuff. So, hopefully that'd be pretty useful for you. Okay, so there you have it. Let's go ahead and dive right into this crash course. Okay, so the first thing I need to discuss is this idea that the Python code is actually the easy part. And what you can see here is some Python code. So this comes from a Jupyter notebook. This comes from Python and Excel. You can see the code is exactly the same. And here's the point. There's not a lot of it. You can see here I have 1, 2, 3, 4 lines if you want to count the comment. And that basically tells you that creating machine learning models, decision tree models, or any other type of machine learning model using Python is actually quite simple. The code is the easiest part. What's actually really super important is for you to understand how they work. Because if you build an intuitive understanding how decision tree machine learning models learn from data, then you will be able to craft the most useful models. Okay, now with that said, that's totally cool. Let's go ahead and jump right into the ML fundamentals, the machine learning fundamentals. And I'm going to assume that most people that watch this video are relatively new, if not brand new to machine learning. If you're not, check out the video chapters below, and you can go ahead and skip ahead to other parts of the crash course. Okay, so first up, what is machine learning? So I'm not going to read you this definition here. You can totally pause the video and read it if you would like. What's actually super important is this idea that this definition, this thinking about machine learning, and by extension, artificial intelligence in general, is nothing new. This was first created in 1959, which is 65 years ago now. So artificial intelligence, machine learning, these ideas are not new. They've been around for a really, really long time, even though it doesn't necessarily seem like it these days. Now, AI, artificial intelligence, has many, many branches, has many, many areas of study. And machine learning can be thought of primarily as the part of artificial intelligence concerned with what we often call predictive analytics, which is, can we use machine learning techniques like decision trees to learn patterns in our historical data and then offer us predictions in the future? Now, I also use the word probabilistic here because every machine learning model is wrong. There's an old adage that says that all models are wrong, but some are useful. That's certainly true in machine learning. That's where this probabilistic thing comes into play, which is that not every prediction is going to be awesome. And you just have to realize that. That just comes with the territory. Okay, so I've used this term, decision tree, machine learning technique, that sort of thing. In computer science terminology, this is what's known as an algorithm. And an algorithm can be thought of in terms of analogy as like a recipe. So I'm not a good cook. I'll freely admit that. But every now and then I want to cook a tasty meal for my partner or for a guest or something like that. So what I do is I go to my bookshelf and I grab an America's Test Kitchen, ATK cookbook, and I flip through it and I have all these recipes. And recipes are awesome. because they are detailed instructions of how to acquire my raw materials, my ingredients, how to prepare them, how to cook them, how to serve them. And what a recipe allows me to do is take raw inputs, do some work to them, and then produce some sort of value-added output. In this particular case, in our analogy, a tasty meal. But it's the same thing in computer science and machine learning in particular. An algorithm is a recipe for taking raw materials, your data, doing stuff with them, and then producing a useful value-added output, which is what is known as a machine learning model. Now, machine learning, as I mentioned before, uses historical data to create a model that is used to make probabilistic predictions. Now, here's the thing. Not surprisingly, because this is such a useful thing, there are many algorithms, just like there are many recipes in an America's Test Kitchen cookbook. And using the right recipe is usually a really good idea. However, there's this key concept that we have to understand. In machine learning, there's this idea known as the no free lunch theorem. And the no free lunch theorem says, look, no single algorithm, no single recipe is guaranteed to be perfect, the best for any given data set. Now, that being said, over the years, we have identified that certain families of machine learning algorithms are more useful than others in certain situations. So for example, when your data is in a tabular format, decision tree algorithms and machine learning algorithms based on decision trees are a good bet, a great place for you to start, state of the art. If you're building a cat video detector, let's say you work for YouTube and you need to detect cat videos, you're probably going to use some form of a deep neural network instead, because that family of algorithms works better for video data than it does for tabular data. Now, not surprisingly, algorithms are all over the place in the modern world. And machine learning algorithms in particular are very powerful and very prevalent. One form of machine learning algorithms, which we're not going to talk about in this video, are what are known as recommendation engines or recommendation systems. So things like LinkedIn decides what posts to show you, and that's the result of an algorithm, machine learning algorithm. Amazon recommends you products. YouTube suggests videos to you, on and on and on. Machine learning algorithms are everywhere. They take many forms. Now, that being said, the focus of this particular crash course is on decision tree machine learning because these types of algorithms allow you to answer very interesting business questions. And that's typically where we see most of real-world machine learning and most of real-world AI, by the way, being realized in most organizations is using machine learning techniques like decision trees to answer questions like this. Can we use U.S. Census Bureau data to predict whether or not someone earns more than $50,000 a year? Now, you might be thinking to yourself, Dave, I don't care about this. This doesn't apply to me. I work in healthcare or government or manufacturing or whatever it might be. That's okay. Think about this. We're going to use this data set in this particular crash course, but what it exemplifies is a more general pattern, a pattern of yes/no questions. And these are everywhere. And they are the single best place for you to start delivering real-world business value with machine learning. So for example, let's say you work in healthcare and you work at a hospital and you have an emergency room. And one of the things that you would really like to know is, can we predict accurately if somebody comes in the emergency room, whether or not they're going to be admitted long-term to the hospital? Because you might need that for staffing or cost reductions or whatever, it might be a really super useful thing to know. That's an example of a yes/no question. And this yes/no paradigm, this yes/no pattern exists everywhere. For example, I built a model for one of the state governments here in the US for predicting whether or not an unemployment insurance claim would be fraudulent, yes or no, right? So these yes/no questions are everywhere. So don't concentrate so much on the nature of the data itself. Think about the general patterns, because these patterns can be applied to any industry, any business domain, anything you can think of. All right, so we got our recipes. We know that they're super useful, and we know that recipes don't work unless they have raw ingredients. And in machine learning, your raw ingredients are data. So let's talk about data. So what we can see here is a subset of the U.S. Census Bureau data set that I'm going to be using in this crash course, in which you will get if you opt to get the files from me as well. You'll get 2 CSVs of this U.S. Census Bureau data. And what we can see here is a certain number of rows and a certain number of columns. But when I think about my data I need to have some terms so that you and I can have a conversation at a high bandwidth. So if I think about my entire collection of data, I could call it a table, a data set, a data frame, a matrix, whatever it might be. So it's basically all of my data. All these terms are completely synonymous, by the way, just so you know, completely synonymous. And next up, we can start thinking about the rows, right? The horizontal aspect. And we might call these rows or examples or observations or samples, all mean the same thing. But what's really super important here is the pattern, not the terminology. When you're doing machine learning like this, every row should be an item of interest. In the case of this particular data set, each row happens to be a US citizen, somebody whose data was collected by the US Census Bureau. If you worked in healthcare, each row would be a patient. If you were that US state government I mentioned, each row would be an unemployment insurance claim. So every row is some logical thing. Now, not surprisingly, if the rows are these logical things, then the columns, the vertical aspect, are the attributes, the characteristics of these things. So for example, we have this column here of marital status, and we might call this the column or a character trait or an attribute or a feature or a variable, all mean the same thing. Okay, so for example, here, these are all the marital statuses of these US citizens in the data set. Now, there is a special kind of column, a special kind of feature in machine learning, which is typically referred to as a label, an output, a target, that sort of thing. And this is a special kind of column because your labels are what the machine learning algorithm needs to use to actually learn stuff. And we're going to go into this in more detail, of course, in this crash course. But the idea is you have to have a label. If you don't have a label, you can't train a decision tree model. Now, when we start talking about our data, we can also start thinking about the contents of these columns, of these features. What is the nature of the data stored within them? And in the case of machine learning, we typically have only two types of data. We have the first kind, which is numeric, and this measures stuff: age, height, weight, price, so on and so forth. So here we can see age, here we can see hours per week, and these are numeric columns, numeric features. Now, we also have categorical data. And categorical data divides things into groups. So for example, we can see here, the marital status column or feature is categorical. It says, look, this particular person has never been married, this person's divorced, so on and so forth. It organizes the individual rows into these groups. And that's all machine learning algorithms care about, by the way, for the most part. Numeric, categorical, that's it. Right? Doesn't matter if the numeric data has decimal points in it or not, doesn't really matter. It's all numeric as far as the machine learning algorithm is concerned. And just like with our meal recipes, we need to make sure that we're using the best quality ingredients to get the best outcomes. And in machine learning terms, what this means is data trumps algorithm. So to expand upon this analogy of recipes in machine learning is this idea that just like you have different types of recipes, you have appetizers and soups and entrees and desserts and that sort of thing, you have different types of machine learning. And first up, what you have is supervised learning. And that's kind of what we've already talked about. And that's where your data has labeled examples. Okay, you have one of those special columns and you've got a label or a target if you're trying to predict like a numeric value. And that's known as supervised learning. And why it's called supervised learning is because the label helps supervise the learning process. And we're going to learn more about that in the crash course today. Next up, we have unsupervised learning. That's another type of machine learning. And unsupervised learning is the collection of machine learning algorithms and techniques where your data doesn't have any labels, which is most of the world's data, by the way. Most of the world's data doesn't have labels. So a prime example of unsupervised learning is clustering or cluster analysis. And I'm going to have a future crash course on my YouTube channel that talks about k-means clustering with Python, which is a form of unsupervised learning. And cluster analysis is something that's very, very commonly done in real-world analytics. I use it all the time in my real-world work. Next up, we have semi-supervised learning, and that's where we have some of our data does have labels, some of it doesn't. And we use the labeled data to try and bootstrap into the unlabeled data. And that's semi-supervised learning. And then lastly, we have what's known as reinforcement learning. And the easiest way to think about reinforcement learning is this idea of self-driving cars. So imagine, if you will, I'm a self-driving car company and I need to start building a car that can drive itself. So how do I do it? Well, one approach might be is to create one of these tabular data frames where I'm trying to encapsulate every single possible outcome that a self-driving car could encounter in the real world, and that's how it learns. Unfortunately, that's not very realistic, because essentially you'd have to have unlimited rows and unlimited columns to capture the real world, because there's just so much complexity involved. So that's not practical. So what you end up doing instead is you define the rules of the system. For example, in the United States, each one of the 50 states actually has like a manual. You can actually go get a manual that tells you the rules of the road. So you think of that as the rules. And what you do is you encode those rules, and then the computer then, first in simulation, starts driving in simulation, and it violates the rules. It breaks the rules. It runs through red lights or stop signs, it crashes into cars, whatever it might be, and it learns that way. And then after a while, once it's learned enough in simulation, you then take it out on the road, usually with a human being sitting behind the wheel to slam on the brakes or grab the steering wheel if needed. And then the car is still starting to learn and learn and learn. And then eventually, hopefully, the car will end up driving itself. So reinforcement learning is this idea of we define the rules of the system, and then the computer learns iteratively through mistakes how to do things. That's reinforcement learning. Now, these days, all of the practical, highly desirable, high ROI machine learning that exists is supervised learning. For example, predicting these yes, no things. Great example. By the way, just so you know, technically speaking, generative AI, LLMs, ChatGPT, that sort of thing is supervised learning. Yes, ChatGPT is a very large, complicated, and powerful model, but it is a supervised learning model. It uses labeled data to learn. So just so you know, even if you want to throw generative AI into practical machine learning, which I do not, by the way, at the time of this recording, it is still supervised learning. So this is all the hotness, right? Predicting things, predicting outcomes, all that kind of good stuff, forecasting, it's all supervised learning. So unsupervised learning is also extremely useful, very powerful. I'll have a crash course on it, like I said, but the hotness is all around supervised learning. Now, in the case of supervised learning, we can break it out into two separate types. So first up, we have what's known as classification. And that's where what we're trying to do is build a machine learning model that can predict categorical labels. And the classic example here is a spam filter. So emails come into your Gmail account and they automatically get labeled spam or junk or not. This is a spam filter. Notice this is a binary or yes/no situation. I told you it's super useful, right? Everybody loves a good spam filter. Everybody loves a good spam filter. So this is a great example of classification. My predictive model, my decision tree model, for example, is trying to predict spam or not. Next up, we have regression. And regression is this idea that we're not trying to predict categorical labels. Our output, our target, our label is actually numeric, like a price of a house, revenue, sales, whatever it might be. And that's also a very common supervised learning technique. Now, generally speaking, you want to prefer in the early days classification, I would tell you, because classification is easier to get right. It's easier to find these really powerful business problems that can be boiled down to yes/no type situations. And this is where you should start. The good news is that decision trees and algorithms based on decision trees can do either classification or regression. So you're kind of covered by learning decision trees. You can do either or, even though you should probably start with classification in the early days. Okay. So as I just talked about on the last slide, machine learning encompasses many different areas of study. We're going to focus on supervised learning in this particular crash course. And we're going to use yet another metaphor, another analogy to help us understand what's going on here. And we're going to use the analogy, the metaphor of a classroom. And in particular, we're going to think of you as the teacher or the supervisor, because you're supervising the learning. And in particular, your student happens to be the machine. Okay? So you're supervising the learning of the machine. And this takes three distinct logical elements and combines them together, this idea of the machine learning classroom. And they are data, algorithm, and training. Okay, so data we've already talked about. We've talked a little bit about algorithms. We're going to go more in depth and build up an intuitive understanding how the decision tree algorithm works. And then lastly, we have this idea of training regimen. And we're only going to briefly touch on that because that's like a whole other crash course. But when you combine these three things together, what you get is a model. That's the intersection here. And a model is a binary thing, like a Word file or a PowerPoint file. You can take a machine learning model, you can train it using Python, you can create the model object in Python, and then you can save it out to a file. Using Pickle, for example. You could pickle it out, and then you could attach that pickle file to an email and send it to a coworker. So from that perspective, a model is a binary thing. It's this, this file, this collection of information that you can actually move around, deploy to your web servers, all that kind of good stuff. So the model is actually the result of all these things. Now, I am bad like a lot of people. I'll talk about, model and algorithm and kind of use these synonymously, but technically speaking, they are separate, right? The model is the intersection of all these things, and the algorithm is the distinct recipe, right? That you would then incorporate into data. You incorporate data into the recipe, excuse me. And the training is kind of like the preparation steps of your recipe. And then the model is kind of like the tasty meal. So these are core ideas. And we're going to explore these more throughout the crash course. Okay. But the most important idea is in supervised learning, you are the teacher and the machine, the computer, your laptop is the student. So you're supervising the entire process. Okay. So what I like about this particular analogy, this particular metaphor, is that there's a lot of parallels. So as a teacher, you have the responsibility of teaching your students, and eventually you need to actually assess whether or not your students have learned the things that you hope they learn, that they've learned the things that they needed to learn. And as with human beings, machine learning has not found a better way than testing to do this. So just like you test your students periodically to make sure that they've learned the things that they're supposed to learn, you also test your machine learning models. And this is all very, very important because what this idea of testing tells you is that one of the very first things that you do in your machine learning projects is you need to start with your entire set of data, and then you actually need to split it. You need to split your data into training data and test data. And once again, using our analogy, you can think of your test data as being like a bunch of questions that maybe the teacher wrote during the summer break. And then they said, okay, some of the questions I'm going to use for homework assignments and quizzes and that kind of thing. And then I'm going to save some of my questions for testing. So that's the way you can kind of think about it by analogy, right? I got my data. I'm going to break it down into training and into testing. And the actual mechanisms by which we do training and test splits is completely beyond the scope of this crash course because the answer of how do I properly split my data, Dave, is it depends. So in the description below the video, I'll put a link to a really good blog post that talks more about this, and you can learn more about, splitting your data if you'd like into training and test data sets. Just know that you have to do it, and you do it at the very beginning of your project. Before you look at your data, before you explore your data, you split it. That's the first thing that you do because you need to have test data to validate that your model's actually learned. Okay, now with that, let's move into our algorithm, decision trees. So decision trees are a fundamental supervised learning algorithm. If you took a university course on machine learning or data mining or anything like that, what you would find is that decision trees are often covered very early on in the course, maybe even first. And the reason for that is they're super intuitive and easy to understand how they work conceptually. And then you can map that to various other things as you dive into more detail. Now, at a very high level, this is how decision trees learn from data. They recursively split your data set, the training data set, into the largest purest groups. And purity is defined very simply as examples, your rows all have the same label. Now, that's a bit abstract, so let's take a look at a decision tree. This is an example of a trained decision tree. And what we can see here is that it's very intuitive to understand how it works. Most people can intuitively understand this even if they've never seen one before or explain how it works, right? They might be familiar with flowcharts or something like that, but conceptually it's really simple, right? We ask questions starting at the top. And then based on the answers to the questions, we move down the tree. So for example, let's say we have a US Census Bureau row of data and we say, hey, is this person married? Yes or no? Let's say for the sake of example, they are married. So we go down this side of the tree. Next question we ask is, what's their gender designation in this US Census Bureau data set? And we say, are they female? And we say, yes, they are designated female. And we move down here and we say, okay. Well, at the very bottom of the tree, this is where we make our predictions. So this tree has learned from the data that married females make more than 50K a year. And ideally, every row of data down here, every married female in the data set, all of them have the label greater than 50K. Now, most of the time, that's not realistic. It's usually 80-20, 70-30, something like that, right? So this prediction right here is really based on majority rules voting. But ideally, the tree is trying to find these buckets down here, these groups, where the labels are ideally all the same. That's 100% pure. If they're all the same label, they're 100% pure. That's what it's looking for. It doesn't always get it, but that's the goal, okay? Now, when we think about our decision trees, we need some terminology here. First up, we have the root. I'm sorry about that. I'm blocking a little bit of the thing here, but you can see it, root. So the root of the tree is this very first decision or question, okay? And every other decision or question more generically is referred to as a node. So this is often referred to as the root node. So it is a node and it's at the very top, so it's the root. And this is a node, but it's not at the top. So it's just called a decision node or a split point. All these kinds of things are synonymous, okay? And at the very bottom of the tree, we have leaf nodes. And leaf nodes are where the predictions are made. And like I said before, these are based typically on majority rules voting schemes, but ideally, what the tree is trying to do is make the leaf nodes as pure as possible, meaning it's trying to say, look, I really want to have only one label in every leaf. And this is still a bit abstract. We got to crawl before we walk and walk before we run. We're going to talk more about how this works in detail in future slides. Now, I've mentioned this before, but I'm going to say it again, and I'm going to explicitly put it on the slide because it's super important. A node is 100% pure. A node, if it's a leaf node, it's 100% pure if all of the labels, if every row of data that flows down the tree and ends up in a particular node, if all of the labels are exactly the same, it's 100% pure. Okay. Now on the other end of the spectrum, if we have 100% pure, we got to have 100% impure. And that's based on the number of labels. So in the case of our particular data set here, the US Census Bureau data set, we have two labels, greater than 50K, less or equal to 50K. And the worst case scenario in that particular situation is if you have a perfect 50-50 split, right? Half the labels are less than or equal to 50K and half the labels are greater than 50K. That makes it like a coin flip, essentially. That's the worst case scenario. Now, to expand upon that, let's say we're trying to build a decision tree to predict Olympic medals, bronze, silver, and gold. The worst case scenario would be a node where we have 1/3 of each, right? All the labels are equally represented. That's the worst case scenario. That is the most impure situation. So what trees are looking for is 100% purity, but they'll settle for something not as good as 100% impurity, but what they're looking for is something better than an equal split of the labels, because that makes your predictions very problematic. Okay, and we're going to see more about how this works in later slides. So when we have a trained decision tree model, we can use it to create predictions on net new data. So let's say, for example, the US Census Bureau starts collecting new data here, and we can see the characteristics of this person. And what we can do is we can then ask the model to make a prediction, because notice we don't have the label here. And what we can say is, all right, is this person married? Yes, they are. Married civilian spouse, so they are, yes, they're married. So we go down, we say, next we say, what's their gender designation in the data? And we can see it's female. So we say, okay, they come here. So we make a prediction of greater than 50K. And that's how the models work. That's the terminology. And what we're going to learn now in slideware in a very intuitive way is how does the decision tree actually learn from the data and create itself? Okay, so we're going to do something that's silly. It'd be absolutely awesome. This is completely silly, but you could do it in Python. You could create a Python data frame like this, and you could ask the scikit-learn library in Python, for example, to train a decision tree off of 4 rows of data, and it will do it. It will say, no problem, Dave, I'll go ahead and do it. It's not a useful model, it's a silly exercise, but technically it's possible. So it's a contrived example, but it is realistic insofar as you could really do it in code if you wanted to. Okay, so this is our data frame, right? We're trying to predict this is our label, and these are all of our other features. So the first thing the decision tree is asking at a conceptual level is, hey, which of these features, which of these columns best splits these labels into the largest, purest buckets? Now, to make this kind of simple in terms of a graphical representation, I'm going to use the idea of jars and marbles, or buckets and marbles. So, how these ideas work vis-a-vis the graphical representation is I have some arbitrary feature. I'm calling it X because it could be anything. And then what I do is I need to put my color-coded marbles in here. And what you can see here is I'm using orange, this reddish orange color, and this green color to represent each of the label types, right? And these will be represented as marbles. So I'll have orangish marbles and greenish marbles. And for every row of data in a table, I will have a single marble represented in these jars, something like this, right? So we can see here, based on feature X, I have 6 rows of less than or equal to 50K over here and 6 rows of greater than 50K. So that's going to be our visual representation mechanism to understand these concepts of splitting the data and purity and all that kind of stuff, okay? It's a very simple representation, but it actually is realistic compared to what's happening behind the scenes with the mathematics, which I'm not going to cover. You're welcome. Okay. So, all right. So the algorithm, the decision tree has to say, look, I need to look at each feature in turn. I got to look at all the features, see how they split the labels, how they split up the marbles, and then I'll pick pick the feature that's the best, right? The one that splits the data the best. Now, generally speaking, all things being equal, the standard decision tree algorithm, which is called the classification and regression tree or CART algorithm, just moves left to right. And some people, maybe you are asking yourself, Dave, should I rearrange the order of my columns based on this idea of going left to right? And the answer is no, don't do that. There's no point in doing that. It doesn't really matter. So just set up your data frame. Don't worry about the column ordering. Everything will work out just fine. The label doesn't have to be on the far right or the far left. The label could be anywhere in the data frame as well. It doesn't really matter. But generally speaking, what we do is we tend to put our labels on one end or the other, and all the rest of the features, it doesn't really matter what order they come into. Okay, they come in. So the algorithm just starts left to right. And the first thing it does is it says, look, I'm going to look at the age feature. I'm going to look at age here. Okay. And right here it says, look, I'm going to use a rule, a decision, a question of is age greater than or equal to 50? Now you might be wondering, how did it come up with this number? We'll get there. On a future slide, I will show you how this actually works conceptually behind the scenes. But for right now, just assume some magic happened and poof, it decided that 50 is the magic number for the age feature. And it says, okay, I'm going to apply this rule to these rows of data and then grab the marbles and then distribute the marbles across the jars based on the rule. So what we can see here is this is the result. Okay, so we say, hey, is this person greater than 50 in terms of their age? Yes, they are. Oh, they have a red marble, or an orange marble. Boop, goes here. This person is older than 50. What's their marble? Oh, they're a green marble. Boop, it goes here. And then you can see 49 and 31 are both less than 50. And we have an orange and a green marble. Boop, boop. And what we can see here is a situation where we have perfect impurity, right? Because we have a 50-50 split, right? It's a coin flip, right? Half the people that are greater than 50 years of age make more than 50K and half of them do not. half of the people less than 50 make more than 50K and half of them do not. So this feature with this rule, with this decision, with this question, doesn't really help us very much in making good predictions. It's basically a crapshoot. It's a gamble. So the algorithm says, cool, I'll make note of that and I'll move on to the next feature. So I'm going to move on to the education. And education is categorical. And what it does is it looks at the various values and it says, okay, I'm going to look at the value of education equals masters, and I can go ahead and split the data. And then based on the data, what we can see here, once again, is another 50-50 split. Okay. Some of the folks with master's degrees make more than 50K. Some of them don't. Same with the high school grads, at least based on this very small data set. So we also can say, this is not great. Algorithm makes note of it and keeps going. And then it looks at marital status, repeats the process, right? Looks at, whoops, go back up slide here. Marital status. And we can see here, oh, well, you know what? Look at this. Look at it. Look at this. Look at this. This is 100% pure. Notice that the only marble in this jar is green. So it's 100% pure. There's not many marbles in the jar, which is unfortunate, but at least it's pure. And over here, notice that the purity is 2/3, right? 2 out of 3 marbles are the same label. Notice that this situation is better than this situation or better than this situation. So at this point in time, the algorithm has identified that this feature of all the ones looked at so far is the best, right? Because this is a crapshoot, this is a crapshoot, this is way better than a crapshoot. But the algorithm's got to keep going. So the next thing it looks at is the racial designation. And it says, okay, look at that. If I divvy everything up, 100% purity. This is awesome. Okay, 100% purity. All the green are in one side, all the red, orange are in the one side. This is great. This is 100% pure. Awesome. But doesn't stop. It keeps looking at all of the other features. It looks at sex equals female. Not great. It looks at hours per week. Decides on a rule of greater than 42. No reference to the Checkers Guide to the Galaxy, by the way. And if you don't get that reference, don't worry about it. Anyway, so it looks at that and it says, this is pretty cool, right? The race equals black decision node perfectly splits the data, all green, all orange. But so does hours per week greater than 42. So the question then becomes, well, what does the algorithm actually pick? And the CART algorithm, the de facto standard algorithm for decision trees, is known as a greedy algorithm. And what it does is it picks the very first feature that it finds that's the best. It says, look, I got 2 features that are tied for being awesome, so I'm just going to pick the one I encountered first, right? That's what it does. It's a greedy algorithm. So that's what it does. So it has now learned that the very top of the tree, right, because we're building a tree from scratch with this data frame here, that the very top of the tree should use race equals black as the root node, as the very first feature in the tree, very first decision point in the tree. But you know what? Let's make things a little bit more interesting, right? We're going to build a tree intuitively in slideware, but 4 rows of data is not enough. So what we're going to do is we're going to increase the data by 50%, all the way up to 6 rows of data. Such a big data set, so huge. Okay, but this will allow us a little bit more flexibility in terms of understanding, building an intuitive understanding. Now, once again, you could totally build a decision tree model using a data frame that looks like this with 6 rows of data. You could totally do it. It's technically valid. It's not useful, but it's technically valid. But what's more important is this example really does teach you enough about how the algorithm works intuitively to use it effectively. So keep that in the back of your mind. This is, you're learning good stuff here, even though we're only working with 6 rows of data. Okay. So this is the same table that we just saw on the last slide. I've just shrunk it down so that it fits on my slide here. The mathematical calculation that is used behind the scenes to embody this idea of the marbles in jars, to embody impurity, is what's known as Gini impurity. And you can think of Gini impurity intuitively as a measurement of the probability that the decision tree made a mistake in a prediction, right? Gini impurity. So high Gini impurity is bad. low Gini impurity is good. Because if your Gini impurity is 0, what that tells you is that there's 0 chance you're going to make a mistake. And that's good, right? 0 mistakes, that's good. Now, this is what happens technically behind the scenes. The algorithm goes through all the features like we just saw, one by one, and it calculates this Gini impurity score for each one of the features. And the one that it picks is the one with the best, that is the lowest Gini impurity score. That's what it does. That's how it works. It goes through them all, does the math, picks the one with the lowest score. Okay. Technically, you don't need to know the mathematics. Like I said, I know the mathematics, but I don't actually calculate them when I do real world machine learning work because nobody cares. What I do is I keep in this idea of impurity in my mind. That's what I really concentrate on. Now, here's what's really cool. This Gini impurity calculation that the tree uses not only takes a look at the raw purity, right? How many marbles are the same color versus how many are not, but also it takes into the number of marbles, which is known as the weight. So what it does is it says, look, if I have one marble in a jar, that's 100% pure, but it's only one marble, so who cares? What I'm looking for is a jar with lots of marbles in it where the jar is pure. Ideally, the labels are all the same inside the jar. So, and this calculation happens for you automatically, and it's what you want to have happen, right? It's the best, it's the most desirable outcome that you're going to see, that it not only looks at purity, but it also looks at the number of rows, the number of marbles in the jar. Okay. So conceptually what we can do here is we can use some gold and green coloring here to kind of divvy up things based on the marital status here. Right? So you can see marital status is here. Is marital status never equal to married? And then we can go through all that. We can see, hey, the green one is yes, and the other ones are this gold color. And then, of course, we have our marble colors once again, and we can put the marbles in there, and we can say, cool. This is pretty good, right? I've got 5 marbles in here, and 4 out of the 5, or 80%, are the same. So that's pretty good purity. Not ideal, but pretty good. Over here, we have 100% purity, but we don't have a lot of weight because we only have 1 marble. That's the conceptual idea. Conceptually speaking, Gini impurity prefers something like this to this because 1 pure marble is not very good, but a lot of marbles that are mostly pure is pretty good. Okay, so that's the core idea here. There's a mathematical representation for all of this, but you don't really need to know it. You could always look it up if you'd like. In the description below the video, I'll give you a reference to a good textbook, which talks about this in more detail, and you can get that textbook and study it if you would like. Okay, so do you remember on an earlier slide where I showed the algorithm going through the age column and it picked a rule saying age greater than equal to 50? And I said, look, later on, we're going to talk about how that rule came into being. This is the slide, and it's all about binning. Now, here's the core idea. Think of an age column or any other numeric column. Now, granted, we only have 6 rows of data here, so it's not particularly large. It's not particularly difficult. But imagine you're talking about thousands of rows, hundreds of thousands of rows. Those kinds of columns, those kinds of numeric columns often have many, many unique, distinct values. So finding the cutoff, finding the rule for a numeric column is a non-trivial task, okay? So what we do, or I should say we, what the algorithm does is it does something called binning. And the process of binning is essentially this idea of trying to change a column of numbers into a series of categorical groups based on some sort of cutoff, right? For example, what we saw earlier, age greater than or equal to 50. So to reiterate this idea, imagine something like this, right? We're going to create a rule, a hypothetical split point, a hypothetical decision around the age column where it says age is less than 30. And I'm going to use these green and gold buckets again, and we can apply the rule to the data, and we can see here what's in gold and what's in green based on the rule. And then, of course, we can then do our marble thing and then split up the marbles. Okay, so the question then becomes, how does the algorithm efficiently find these thresholds for the rules, right? How does it know to use age equals 30 or age equals 50 or whatever it might be? So what we do is, once again, we're we're not doing anything, by the way. This all happens behind the scenes, right? You're standing on the shoulders of giants here using other people's code. Is that the algorithm finds split points. And what we're going to show here on this slide is an intuitive understanding of what's going on behind the scenes. Now, to be crystal clear, there are some other computer sciencey optimizations that are going on as well. And what that does is change things a little bit. However, conceptually, what you're going to learn in this slide is enough to understand what's going on behind the scenes. Okay, so what happens is that the first thing the algorithm does is it takes a copy of that numeric data and then it sorts it. And typically it's ascending order. So you can see here that the original values here have been copied over here and arranged in ascending order. And then conceptually, intuitively, what happens is a bunch of split points are calculated based on the differences between these. So conceptually, I have a split point here, a split point here, a split point here, so on and so forth. Once again, like I said, there's actually some more computer sciencey stuff that goes on behind the scenes, but this is the gist of what the computer is doing to try and find an optimal threshold, an optimal split point in a column of numbers. Okay. And what ends up happening is these split points are exactly what you think. They are defined as the midpoint between these numbers. So for example, this guy right here is midway between 28 and 31. So what's halfway between 28 and 31? 29.5. Rounded up, 30. So that's essentially the logic that you get. So you get this kind of situation where there are 6 numbers and the algorithm through this process finds 5 split points. Now notice this. This is super important. This is the gist of what we want to understand from this slide. Because of what goes on behind the scenes in the bidding process, the number of split points that are considered for a column of numbers is smaller, almost always smaller, than the original number of values in the numeric feature, in the numeric column. So you can see here that we have 6 numbers and we only have 5 split points, which is this idea. In actuality, in many, many cases, it's far less than this. Like you might have 10,000 numbers, but you only need to evaluate 1,000 split points. So the computer is smart, the algorithm is smart, it tries to be very, very efficient, but it still has to go through a lot of different checks. It's got to experiment essentially with a bunch of different thresholding points for a numeric feature and find out which one produces the lowest Gini, right? The lowest Gini impurity score. And this is done every single time for every single numeric feature in every single split point in the tree. I'm going to talk a little bit more about that in a bit. But let's imagine that, if we will, that these are our split points. So what's actually going to go on behind the scenes can be represented graphically like this. Notice that each one of these represents one of the split points that we saw, one of those orange triangles that we saw on the previous slide. 30, 35, 40, 51, 53. And then what the algorithm does is essentially does the marble thing conceptually. More specifically, it does the Gini impurity calculation. And these are the results that we get. And without going into all the mathematics, what we can see here, what we can say here is that these two are found to have the best overall Gini impurity scores because of this combination of weight and purity. Now, what's super interesting is that notice that these guys right here are mirror images of each other. In terms of the mathematical calculation, doesn't matter. They come out with the same score, even though they're mirror images of each other, which kind of makes sense if you think about it. And once again, of course, if both of these are tied for be the best, we know that by default, the CART algorithm will actually pick this one as being the winner, okay? Because it was the first best split point found for age, and that becomes the Gini score that is recorded for age, and then the algorithm goes and looks at all the rest of the other columns as we've seen before, okay? A lot of work goes on behind the scenes, right? Remember we saw 4 lines of code earlier? All this stuff happens in those 4 lines of code. This and a bunch of other stuff, right? So a lot of work is going on behind the scenes. Now, what's super awesome about this is, and I mentioned this earlier, but it bears repeating, this process of binning happens with every numeric feature at every split point in the tree. which is great. Because sometimes people, when I teach them this stuff, they get a little bit nervous and they say, hey, Dave, I don't want to trust the algorithm. I don't want to trust it. And I totally get that, right? There's this idea of control. And what they want to do is they want to bin their numeric features at the very, very beginning, right? They want to feed in the bin numbers to the algorithm. And you can certainly do that. However, I will tell you, please don't do that. Because of this idea that the binning happens over and over and over again throughout the tree, the algorithm is essentially creating optimal bins for you at every point in the tree, which is something that is impossible for you to do up front. So don't manually bin your trees. And my apologies, unfortunately, I'm blocking a little bit of this text right here out with my image. If you get the slides, of course, you'll have you'll have the raw text. But the raw text basically says what I just said. Don't bin it yourself. The algorithm does it over and over again. That's actually better. Okay, so now we know how the age feature is being used. So what we saw here on this slide and in the previous slide is, since we're building a brand new tree from scratch with those 6 rows of data, that huge data set, the age feature is the first thing that's looked at. And because of the binning process, age less than or equal to 30 is the split point, the threshold that is chosen for age to say, look, should age end up being the best split point, having the lowest Gini, the rule that'll be at the root node of this brand new tree will be age less than 30. And if it's not the best split, let's say another feature is actually better, then that will become the root node of the tree. So right now, age less than 30 is in contention for the beginning of the tree, for the root node of the tree. Okay, so moving on, as we know, the tree just starts going through the features left from right? And I'm not going to go through every single one of these again because we've seen that already, so there's no point in me doing that. So let's just consider that it goes through and it looks at age, as we just saw, does education, does marital status, and then it gets to the racial feature here, and it evaluates race equals black. And what it can find here is that, wow, this is a really, really good split, right? It's pure on this side. And again, you can see that I'm blocking a little bit of this, so I apologize, but you'll get the slide and you can see the whole thing. And we can see over here that this is pretty good. 2 out of 3, 100% pure. Awesome. And then, as usual, it says, look, I'm going to record that and I'm going to keep going. I'm going to look at some of the other features, okay? And let's say it looks at sex and hours per week, and then eventually it comes up with hours per week and it says, look at this. This is tied, right? Notice that, once again, this is a mirror image of this. So they have the same exact Gini impurity score. And these are both the best out of all of the features, even better than age less than 30. And the algorithm says, cool, you know what? I'm going to pick by default race, the race feature, because it was the first one I found. And CART, the de facto standard decision tree algorithm, is greedy and picks the first one it finds. So we now have the root node, or the very top of the tree. It started with age, went across all of them, found that race and hours per week were the best features. They were tied. Race was the first one, so that becomes the root node. So graphically, we can represent the tree so far, having learned from the data, like this. Okay? It is the root node. Race equals black. Now, this is what's super important. Behind the scenes, the decision tree says, I don't know if I'm done yet. I don't know if I can build a bigger tree and do a better job of splitting the data. So I need to try. So what I do is I take my original data. In this case, we have 6 rows, right? Huge data set. And I flow the rows of data down the tree based on this node here. So what I do is I say, okay, cool. So all the folks with the racial designation of black in the data set go down this side of the tree. And all of the folks with the racial designation of non-black, or white in this particular case, goes down this side of the tree. So notice we have 3 rows here and 3 rows here. This is a contrived data set to make it balanced. Doesn't necessarily mean it's always going to be balanced in the real world. You don't need to worry about that, because what we're talking about is an intuitive understanding here of what's going on, not the exact algorithmic executions and all the mathematical calculations. So the data flows based on the decision node, based on the rule to the left and right. And I'm going to zoom in on this a little bit because it's a little hard to see. But what we can see here on the right side is all of the rows that have a racial designation of not black all have the same label value. And because they have all the same label value, it's pure. It's pure. And the algorithm says, look, I don't need to try and split this data anymore because it's 100% pure. I'm going to make this a leaf node, essentially, because I can make a prediction here. And I will predict always less than or equal to 50K, because that's what all these labels are. They're 100% pure. So I can make this a leaf node. This could be a prediction spot. Now, comparatively speaking, on the left side of the tree, what we can see here is, in fact, that we don't have purity. We have two rows that have one type of label and one that has another. Now, based on the training regimen that you get by default with decision trees in scikit-learn in Python, this will actually be tried to be split again. The algorithm will try and split this data again because it's not pure. It's pure over here, so it's just, on the right side, so nothing to worry about. But over here, I'm going to try and split it again. Okay, so let's think about what that will look like. Okay, so how we can think about the second split on the left side of the tree is working is by taking a look at the impact of the root node split on our original data frame here, our original set of data. So what I can do here is mask out. I can cover up the various rows and the columns to show you what data is now available to the decision tree algorithm for the left side of the tree to try and split the data again. So what we can see here is that 3 rows have a racial designation of not black. This one, and this one. So we can just cover those up. We can mask them out. So conceptually, these are now gone. They're handled by the right side of the tree. It's good. Now, the other thing that we want to also think about is the race feature. Notice that all of these values are the same, which makes sense, right? Because all the folks with the racial designation of black ended up going on the left side of the tree. And we can see here, sure enough, that this feature has all the same value. Now, the logical implication of this is this information is not useful for splitting the data anymore because all the values are the same. So what we can say conceptually is that all the information of the race feature has now been used up in the left side of the tree here. So we don't care about it. So we can mask that out as well. The algorithm won't actually try and calculate a Gini impurity score for the race feature because it's pointless. The values are all the same. Okay. And what we get now is these features are available for the next split, and these rows are available. And what we can see here is that we have these particular labels again, right? Green and orange here. Now, the algorithm is iterative. It just repeats this process again. It's always the same thing. It's always the same thing. We start from the left. We do the age thing. We do the binning process that we learned about before. We get this particular split, which is very, very good, right? This is 100% pure. Love it. But the algorithm doesn't stop. It looks at education. It looks at marital status. It looks at sex. It looks at hours per week. And hours per week looks really, really good here as well. So the algorithm says, look, I got a tie here. Age less than 30 based on the binning process is really, really good. And hours per week less than 43 is also very, very good based on the binning process. So once again, the card algorithm by default greedily picks the age feature and says, look, that's the one that I'll use. Now, once again, this logic can be incorporated into our visual representation of the tree to show its growth, to show how it's being built. So what we can see here conceptually is what we saw before, right? The data for this side of the tree, the data for this side of the tree, and then we can add another split point. So this data got split optimally by using age less than or equal to 30. And then once again, the data flows down the tree like this. And I won't zoom in because it's pretty easy to tell that now that these guys are all the same label and these guys are all the same label. So the tree is done. It split the data perfectly. Every row in every leaf node, because this will be a leaf node, this will be a leaf node, this will be a leaf node, are all the same. Now, to be honest with you, this is a contrived example to be sure, because in the real world, this almost never happens, this situation. But we're trying to build an intuitive understanding. So we can clean this visualization up a little bit, and the tree actually looks like this. This is our fully trained tree. And what we can do is we can say, okay, great. With that tree now built, we can use it to make predictions on new data. And we can see here a new row of data. So the first thing we do is we run it through the tree, and the tree says, hey, what's the racial designation? Is it black? Yes, it is. So we go down this side of the tree. We then ask, hey, how old is this person? Are they less than 30? And they are actually 49. So that's no. So we go over here and we say, yep, based on our data, we're going to predict that they make more than $50,000 a year. Now, while this is a contrived example and it's very illustrative of teaching you the intuition of how decision trees learn from data, it's also emphasizing a very, very important point. Your machine learning models only understand the world based solely on the historical data that you give them. As we saw earlier, this training data set that you create at the very beginning of your project, that's all they know. So if your data is extremely small, or it's extremely biased, or it doesn't have every permutation of your business process outcomes or anything like that, it's going to learn only what it can learn from the data that you give it. So for example, this is basically saying, look, anybody in the United States who is not have the racial designation of black, they always make less than or equal to 50K, which, if you know anything about the US economy, is completely bogus. But this is reasonable for the tree to learn based on the data. So once again, data trumps algorithm. You want to make sure that your data sets are rich, lots and lots of features, lots and lots of rows. But most importantly, what you're trying to get in your data sets are all the different permutations of the possibilities of your business process, so that the decision tree has the possibility of learning them, and that will make for the best predictions. Okay, so trees grow. But one of the things we want to know, obviously, as machine learning practitioners is, when will they stop splitting? When do they actually stop splitting the data? When do they stop growing? Now, we have already seen one case where this is true. Decision trees will stop splitting, they'll stop growing when a node is 100% pure. Now, that can happen. It certainly can happen, but it's typically not the norm. So that's the first condition. It's kind of like the happy path scenario, but not necessarily the common scenario. Now, another case where decision trees stop splitting, they stop growing, is when the labels are all the same. Excuse me, when the labels are different, but the values of the features are all the same. And that's a little bit abstract. So let's use an example here. So here's an example. What we can see here is I have two different labels, but all of the feature values are exactly the same. Now, let's think about this logically. What we can see here is that I have a 28-year-old person with a high school graduate in the United States. They are married, civilian spouse, racial designation is black, they are female, and they are 40 years of age. Now, is it entirely possible in the US economy, where you have 330 million-ish people, that this would happen? Of course. I mean, just by the law of large numbers, you're going to see something like this. But the decision tree in this case absolutely knows, the algorithm doesn't know what to do, right? Because they're like, look, I can't split this data any further because all the values are the same. So that's another stopping condition. Also, not very common in practice, entirely possible, but if you have lots of features, it's going to be exceedingly rare that this actually happens. Now, the single most common reason why your trees stop growing is because of the training regimen. Remember I said, we'll talk about training later. This is when we start talking about it. So machine learning algorithms have these things called hyperparameters, which is a kind of a cool name if you think about it. But the easiest way to think about it, once again, is via an analogy, via a metaphor. You can think of hyperparameters as being like knobs and dials at your disposal for changing the final shape of the decision tree, the final output of the model. And in this regard, a useful metaphor is to think of a soundboard. So like this is a soundboard, like in a recording studio. So I'm wearing a Metallica t-shirt. Metallica's in the sound booth. They're recording a new album. And there's a sound engineer. And the sound engineer is moving these knobs, turning these dials to change the way the music sounds, to change the final output. That's the way to think about hyperparameters. You, as the data scientist, can change the hyperparameter values and actually affect the resulting decision tree model. Now, here are some examples of hyperparameters, okay? You can explicitly say, look, the max depth of the tree is this amount. So the tree can be 5 levels deep and no deeper. And if you have a big enough data set, you will always get a tree that's 5 levels deep and only 5 levels deep. That's a knob, a dial, a setting that controls the final output. That's one of the most easy to understand of hyperparameters, but there are many, many hyperparameters available to you on your decision trees in Python using the scikit-learn library, which is a very common library used for machine learning in Python. And there are some others listed here. You can pause the video and take a look at them, but all of them have the net result of controlling the tree. And what I'll do is I'll put a link down below in the description of the video to the documentation for the DecisionTreeClassifier class, which is a class in scikit-learn for decision trees that do classification problems. And you can see the documentation for all the different hyperparameters and what they do and that sort of thing. So these conditions control the size of the tree. Now, here's the thing. By default, the hyperparameter values on a decision tree classifier in the scikit-learn library in Python allow for very, very large trees. Usually you don't want to use the defaults. You want to adjust the defaults to arrive at an optimal collection of values based on your individual data set. That process is known as hyperparameter tuning, and I might do a video later on to talk more about it. Unfortunately, we can't fit it in right now because that would be its own crash course. But hyperparameter tuning, you can Google it or you can ask ChatGPT about it and you can get some more information about it. But that's the process of adjusting these knobs and dials to make your decision tree model optimal for your particular data set. All right, now you know intuitively how decision trees learn from data. So let's talk about the nuts and bolts of actually building decision tree machine learning models in Python. So as I mentioned before, what we've been studying, what you've been learning in this crash course is an algorithm called CART, classification and regression trees. The CART algorithm is the de facto standard. Now, what's also something I've mentioned is that the scikit-learn library in Python offers a class called the DecisionTreeClassifier, right? It creates decision trees that does classification problems. And it's based on CART. It's based on CART. It's not actually exactly the same as CART. So there are some differences. Now here's the thing. The reason why I teach the CART algorithm in this crash course is because if you happen to use any other technology, R, SAS, Alteryx, something like that, more than likely the implementation is going to be the CART algorithm as described. So it's best for you to learn the general concepts and then the specifics of Python afterwards. And that's exactly the approach I'm taking here. So the first difference between the CART algorithm and the decision tree classifier is that the decision tree classifier only works with numeric data. So if you have categorical features represented as strings, they don't work, especially for older versions of scikit-learn. Like for example, the version that's included with Anaconda Python doesn't work with categorical features out of the box. That are textual categorical features out of the box. That might change in the future, but right now it doesn't work. So what you need to do is you need to transform them or encode them. That's what this means here. Okay, and I'll teach you about that. It's not as hard as you might think. And the next up, and this gives some people some pause, but really in practice it's not that big of a deal, is that when there is a tie between two features that have the exact same Gini impurity, the decision tree classifier picks one at random. Now, the reason why this is not that big of a deal is because in a non-trivial real-world data set, the probability of this actually happening is extremely small. Extremely small. Now, I'll show you in the code samples here in a bit that if you really, really don't like this, you can actually make sure that it's not actually, the randomness is actually controlled, is what I'm going to teach you how to do, how you can control the randomness and get reproducibility. So if that's a big deal for you for whatever reason, you can control it. Okay. Now, getting back to this idea of textual features, textual categorical data can't be used directly, we're going to talk about something called one-hot encoding. And this is the way that you transform your data. Okay, so let's take a look at that. Okay, so what we can see right here is some code where I'm going to my training data set. So this is a data frame. And I'm accessing the race feature, and I'm asking for the value counts, which says go through that entire column of data, find every unique value, and then count up how many times each unique value shows up in the entire column. And I've also added a parameter here called drop NA equals false, which says also count up any missing data, because by default it ignores missing data. So this actually will tell you how many values are missing. And you can see the output here. First thing we notice is that we have no missing values, because we would see NaN, which is the pandas representation of a missing value. So we don't see that. So we have white, black, Asian Pacific Islander, American, Indian, Eskimo, and other, and we can see the counts here. Cool. Now, these are the string values and the counts of the string values, and we know that we can't actually use these directly. So what we do with one-hot encoding is we take each of these unique values here, and then we transform them into their own dedicated features. And that's a bit abstract, so let me show you what this means in terms of a table. Notice here that white becomes its own feature. Black becomes its own feature. Asian Pacific Islander becomes its own feature, so on and so forth. And then what ends up happening is you get a set of binary indicators. So first up, when we have a string-based categorical feature, or actually it could be a numeric-based categorical feature as well, by the way, but it's easy to think about in terms of strings. So we get 1, 2, 3, 4, 5 unique values. We get 1, 2, 3, 4, 5 unique new columns now. So we get a category for we get a new feature for every categorical level or every unique distinct value. And then we get binary indicators. So for example, on this row, this person had the racial designation of white. This one had the racial designation of black, so on and so forth. This process of taking this original string column and essentially pivoting it to be a wider version, right? So we take all the values and then boop, spread them out. This is one-hot encoding. And the easiest way to perform one-hot encoding, it's not the only way, but the easiest way to get started with it is to use a method from the pandas library called getDummies. getDummies. And here's some code. So here's the getDummies function, right? Because you typically import pandas as PD. So pd.getDummies. I want to call the getDummies function. And I would like to perform one-hot encoding on the race feature of my adult census training data set. And what I get back out of this is another pandas data frame, which I'm calling race_encoding. And if I call head on it, you can see, sure enough, boop, 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 right? 1, 2, 3, 4, 5 features, just like we saw. And we see the racial indicators right here, so on and so forth. Now, here's the problem though. When you do this one-hot encoding, it takes the raw string values and makes features out of it. So for example, I actually get a feature here called other. Now, the reality of the situation is for very large and complicated data sets, you might see the word other multiple times, right? Maybe feature A has another bucket. Feature B has another bucket. Feature C has another bucket. So what other is the other? Which other does it belong to, essentially? So what we want to do is actually add a prefix to our column names when we want hot encode so that we know where the feature originally came from. So that's a bit abstract, so let's look at some code. What we can see here is the same code that we saw on the previous page, but notice I've added a new parameter called prefix and say, look, prefix all the column names after the one hot encoded with race. And you can see that right here. So this particular feature came from race. This particular feature came from race. This particular feature came from race, so on and so forth. You want to do this for your own sanity. Okay? Trust me on this. Your future self will thank you for doing this. Okay? So just so you know, the default separator when you use a prefix is an underscore. You can change it, but don't, because it's common coding convention in Python to use underscores to separate logical words in your names. So just leave the default, okay? Now, we can also one-hot encode multiple features simultaneously. And what you see here is some code. The way I typically code things up doesn't mean you have to write your code this way. And you can see here what I'm doing is I'm creating a list of my categorical features. Just to make sure everything fit on my slide, I'm only using 2 categorical features, but I could put 4, 5, 20, it doesn't really matter. However many. And I've got that as a list, which I'm calling cat_features. I can then pass that into my call to get dummies here, right? Hey, hot encode the columns that are in this list, right? Race and sex. And then also prefix those columns with race and sex. And I run all this code. If I run head on it, you can see here that sex female, sex male, race white, race other, so on and so forth. Now here's what's super important. You can't really tell, but what I've done in the Jupyter Notebook output is scrolled all the way to the right. Because if you remember, originally the last column in our data frame was the label column, less than or equal to 50K. And what ends up happening is when you one-hot encode things, is the features that are one-hot encoded get plucked out of where they were originally, and then the one-hot encoded representations are added to the end. So you won't see race anymore as a column on the data frame because it's gone, right? It's now been one-hot encoded. It's been replaced by these representations, which is exactly what you want. And also notice what I'm doing here too is I'm just passing in the entire adult trained data frame. Get dummies is smart. If you pass it in an entire data frame, it will only one-hot encode the things you explicitly tell it to one-hot encode, and it'll leave everything else unchanged, which is nice. So when you're ready to build your machine learning model, it doesn't matter what technology you're using, this is a universal thing that you need to do, is you need to prepare your data to be fed into the algorithm. So in the case of scikit-learn, for example, like a decision tree classifier, we want to one-hot encode all of our categorical features. And what you see here is some example code that demonstrates this. So first up, I'm going to create another list, which is all of my features. So I'm going to build a machine learning model with 1, 2, 3, 4 features here. In particular, I'm going to build a decision tree classifier with these 4 features. Now you may be asking yourself, hey Dave, why these 4? Why only 4? And the answer is so that it fits on my slide. However, it is common in real world machine learning to have like a very wide data frame. And in the early days, maybe you don't use all the features. Maybe you use a subset. So this would be an example of that. So I'm using a subset of the adult census features here: age, education number, marital status, and hours per week. Now, of all of these features, this one is categorical, right? This is the only one that we're treating as categorical. So we need to one-hot encode it. And what you can see here is my code. I'm taking my adult trained data set. I'm subsetting it to only these 4 features. And of these 4 features, I'm saying, hey, one-hot encode marital status and prefix it with marital status. Now notice here I have to put this in a list, even though it's a single item. That's just the way the function was written in pandas, okay? And what I get back is a data frame, as we saw before. And in this particular case, the data frame, by naming convention, we call underscore X, typically underscore capital X. And that is a naming convention in scikit-learn. You can actually call this whatever you want, but by convention, we say it's underscore X. And X denotes our predictors, not the labels, but our predictor features, okay? So this is everything excluding the labels that we want to use to train the machine learning model. In this case, we can see here I have age unchanged, education number unchanged, hours per week unchanged, and then marital status. There's actually a lot of marital statuses. This is only a subset, but they're all one-hot encoded. Okay, so this data frame is good to go. Now here's what's really interesting though. You remember the labels? Our labels were also string values. Less than or equal to 50K, that's string, or greater than 50K, that's string. So once again, we also have to encode these as well. We have to encode our labels because they're string values. So we can actually use a handy dandy class from scikit-learn called the label encoder, and the label encoder will actually do this for us. So all I do is I import my label encoder, I instantiate it, and then I can call fit underscore transform. Now this is another naming convention in scikit-learn and Python that you need to understand. So fit, you can think of as meaning as go learn from the data. Go fit yourself to the data, go learn from it. And then transform says, look, everything that you've learned, go apply it to the data. So fit and transform does two logical things in a single step. So it says, hey, go look at all the labels, learn what you need to do with those labels to transform them from their string representations to numeric representations, and then transform them. And then by convention, we call the results of that underscore lowercase y. Lowercase y is the thing that we're trying to learn how to predict. In this case, it's the label. And what I can do here is I can show you, hey, label encoder, what were the original classes? And you can see here the string values. Less than or equal to 50K, greater than 50K. And then I can also say, hey, what's the mapping? And what I can see here is that less than or equal to 50K was mapped to 0. Greater than 50K was mapped to 1. Now, a couple things that we need to know. First up, these assignments from the original string values to numeric representations is based on alphanumeric sorting. Because notice that in alphanumeric sorting, this value comes before this value, which is why it's 0 and this one's 1. That's the first thing. Second thing is, if we have more than two labels, let's say we're doing Olympic medals, bronze, silver, gold, you'd have 0, 1, and 2. If I had 4 labels, I'd have 0, 1, 2, and 3. So it scales. The same code scales to the number of labels. Doesn't matter how many you have, it works, okay? So we're good to go now. We now have our labels encoded. We have our data prepared. So now we can actually train a model. And here's the code for training a model. And this is code we saw earlier. So let's talk about this step by step. So first up, as I mentioned before, decision tree classifiers in Python and scikit-learn in Python, their default hyperparameters allow for immensely large trees to be grown. And that's typically not what you want. So I mentioned that you have to tune them. So what I've done here is actually picked a hyperparameter value for you just to demonstrate things. And that's right here. So what we can see here is I've imported my DecisionTreeClassifier class and I'm instantiating it. Now the parameters that you pass to a scikit-learn object that embodies a machine learning algorithm, for example here, a decision tree classifier, these hyperparameters define the training regimen. Defines how the tree gets trained, defines the final shape of the model. Okay, so this pattern is the same no matter what machine learning algorithm that you're using. The actual parameters will be different, of course, for different algorithms, but conceptually they're exactly the same. And what I'm doing here is I'm picking a particular hyperparameter and I'm saying, look, you can only create a leaf node. The tree can only have a leaf node if there's at least 3,000 rows of data or more in the leaf node, which is a lot, right? 3,000. And what that does is it says, look, it constrains how big the tree can get, because the bigger that number for min samples per leaf, the smaller the tree. The smaller the value of min samples per leaf, the larger the tree. And once you get the code from me, you can play around with this and you can actually see for yourself how it changes. Okay, so we need to have at least 3,000 rows or 3,000 observations to make a leaf node, which controls the size of the tree. This will make the tree actually relatively small. And I'm only doing that mainly so that it fits on my slide, so that you can actually see the visualization of it. Okay, now I mentioned earlier this idea that in case of a tie, the decision tree algorithm will pick one of the features at random. And I said you could control that. And the random state parameter is how you do that. What the random state says is that, yes, the algorithm is still going to pick a feature at random, but every time you run this code cell, it will always pick the same thing. It will always pick the same thing at quote unquote random. That's what this means. So notice here I've just picked an arbitrary value of 1, 2, 3, 4, 5 to illustrate the point that this is simply just to control the randomness. And you do this mainly for reproducibility. So I set the random state in my courses when I teach them because I want my students to see the same thing that I'm showing them on the screen or in my code. So we have to set the random state so we all see the same thing. Okay, cool. So I set up my tree, right? Set up my tree with a training regimen. So this is my algorithm, right? Decision tree classifier is my algorithm. This is my training regimen. And I get back an object, which I'm calling tree_1. Terrible name. This is a terrible name for a decision tree. Pick a better name, please. Okay, cool. So I've got my bad named object here, poorly named object. And then what I do is I call fit on it, which says go learn from the data. And this command right here, this line of code, does everything that we've just learned about. Everything you just learned about. All that process of binning and splitting and all that kind of stuff. This is when it happens, is when you run this fit. And you have to pass in your predictors, right? Your features, and then you have to pass in your labels, obviously. Otherwise it doesn't work. And this runs, and this is the output that you see. Okay, so now you've got a tree. With your decision tree trained, now what? Well, of course you can make predictions with it, but typically what you do most of the time is you want to understand the structure of the tree. You want to examine the tree to produce insights. And the easiest way to do that is to visualize the tree. So what we can see here is some code to visualize the tree. I'm importing a particular function from scikit-learn called plot tree, which plots a tree, surprisingly enough. And I'm also importing pyplot here simply so I can set the figure size. This is something you're typically going to want to do when you visualize your decision trees in Jupyter Notebooks, for example, to make sure you can control the output. So this code right here will come in super handy. And what we can see here is I'm invoking the plot tree function, and I'm passing in a bunch of parameters to control how the visualization looks. First up, I got to pass in my model, the tree to visualize, not surprisingly. And then next up, what I'm going to do here is change out the visualization. So for example, by default, what you will typically see in a visualization isn't super useful. So for example, what you'll see by default is 0 and 1 for the prediction labels, not the original class labels of less than or equal to 50K, greater than 50K. So this particular code right here allows you to display the original class labels, which is useful from a business context. Now, depending on what version of scikit-learn you're using, you might need to use a list here or not, depending. Okay. After that, the next thing that we're going to do here is we're going to use the actual feature names. So what we do is we grab the column names from our adult_x data frame so that we actually use the feature names as opposed to the feature positions. You almost never want the default here. It's unintelligible. In the next step, we're going to set the font size, which just controls how big the letters are. And then lastly, I'm going to set filled equals true, which color codes the visualization, which actually becomes super useful. So if you run this code, and you'll get this code, by the way, if you get the files, you'll get the Jupyter Notebook with this code in. And if you run the Jupyter Notebook, this is what you're going to see. This is the visualization. And there's a lot going on here. So let me explain how you read this. So first up, by convention, everything to the left means yes. And everything to the right, everything to the left implies yes to the decision node. And everything to the right implies no to the decision node. Okay, so first up, notice our root node here is the one hot encoded feature, married civilian spouse. Now, since this feature is one hot encoded, it only has two values, 0 and 1. So what this is asking is your value less than or equal to 0.5? And since we know the only two values are 0 and 1, this is actually asking, is your value for this feature equal to 0? If it's yes, go down this side. If it's no, go down this side. So essentially, are you married civilian spouse? Is that your marital status? Yep. Or is your, let me rephrase that to be crystal clear. Is your marital status equal to married civilian status with a value of 0? And if the answer is yes, that means you don't have this particular designation, go down here. Otherwise, go down here. Or essentially, if you're not married, go down here. And if you are married, go down here. Well, I shouldn't say that, because there are many forms of married in the data set. But hopefully you get the idea. Okay, now next up, we can just start walking down the tree and see, well, the very top most important feature was this. Over here, for those that have a 0 value for this feature, this is the next most important feature, which is age. And over here, it's education num, so on and so forth. Now, what we typically do is, first up, we don't necessarily look at all of the paths through the tree. Because if your tree is non-trivial in size, there'll be many, many paths, and that's really hard to do. So what we typically start with is actually looking at the leaf nodes. That's what we typically look at first. And when we look at the leaf nodes, notice the first thing here is you get a Gini impurity score. And remember, less is better. So we can see here that this particular node has a Gini of 0.143, which is pretty low. And notice that the color of this node is dark orange. And I'll talk more about why that is in a second. Okay, next up, what we can see here is the samples. And this is the count of the observations. This is the number of rows that ended up in this leaf node. Number of rows that float all the way down to the tree to the leaf. Now remember, I specified that you have to have at least 3,000 rows. And notice here we have 3,051 rows. Okay, cool. Now next up, I'm going to go over to the blue side. And let's look at this dark blue node. Now notice that this dark blue node also has a relatively low Gini, 0.173. Okay. Now, what I want to show you though is this value thing here. Now, this is a little bit complicated. People often, when I teach this in my live classes, I need to explain it a couple times. So I'm going to try to explain it the best I can. Don't be afraid to pause the video and rewind it. All right. So this leaf node has a total of 3,380 rows in it. Okay, that's how many rows float all the way down to the tree, all the way down to the leaf node on the right side of the tree. Now, if I add this value of 323 to this value of 3,057, this total is 3,380. So this 3,380 is now broken up over these two values. And here's the thing. These values represent the labels, right? So notice this is a list. So this is position 0. And as you recall from our label encoder, position 0 corresponded to the label less than or equal to 50K. And position 1 here corresponded to the label greater than 50K. So this node has 3,380 rows, of which 323 of them had the label less than or equal to 50K, and 3,057 had the label greater than 50K. And notice that finally we get the predicted label. And notice that this leaf node predicts greater than 50K because the rows of data that ended up here are overwhelmingly greater than 50K rows. Reflexively, if we go over here, notice that the dark orange here are overwhelmingly this leaf node is overwhelmingly populated with 2,815 rows of data with less than or equal to 50K label. And very few have the greater than 50K label, which is why we predict less than or equal to 50K. So the color coding is really super useful because it shows you the intensity of one label or another. And if you have multiple labels, what you would see is multiple values here and more colors, essentially. So this is how you interpret this particular visualization. And like I said, we usually start with the leaf nodes. And then if we're interested, we can work our way back up through the various paths. And notice that these values change because, for example, we need to aggregate up all of these rows to this node, right? Because we had 8,864 rows, some of which went here, some of which went here, right? So as we go back up, we have to aggregate the rows back up. And that's how you interpret a decision tree. So continuing with our classroom analogy, we talked much earlier in the crash course about this idea that as a teacher, you need to test your machine learning models to understand if they actually learn, because the machine learning model, the machine is your student. Now, to extend this metaphor, extend this analogy, imagine a university course where the professor says, I don't care if you show up for class. I don't care if you read the book. I don't care if you do the homework. I don't care. 100% of your grade is based on your final exam. I actually had a professor like this in my undergrad. So that's what you want to think about in terms of your machine learning projects. You use your test data set once and only once at the very end of your project, and it's like a final exam that's 100% of your grade in a university course. Because the test data set, the performance of your model against the test data set is your final decision point of whether or not you've created a useful model. So you can only take the test once. If you take it multiple times, you run into a problem called information leakage, and it's just a bad idea. So don't do it. Okay, so how do we test our model? Well, first up, we got to grab our test data set. Because remember, early on in the crash course, I told you have to split your data into a training set, which you use to build your models, and then a test set to test them at the end. So in the files, if you decide to get them from me, I will send you a CSV of both training and test data so you can replicate what you see here. Okay. Now, the first thing that we have to do is after we load up our test data set, either from a CSV or a database or wherever, we have to prepare it. So for example, if we one-hot encode things for our training data set that we use to build our model, to train our model, we have to do the same thing to the test set, right? So one-hot encoding, any sort of transformations that we do. And what we can see here is exactly that. So I've loaded up my data frame, my test data frame. This is the same 4 features that we used to create the decision tree model. And we're going to go ahead and one-hot encode marital status. And then what I'm going to do is store that in a data frame, which I call adult_test_x, right? Because these are my test predictors, not my test labels, but my test predictors. Okay, cool. And if I call head on it, you see that the data frame structurally looks just like what we saw previously, right? Same number of columns, same names of columns. The order technically doesn't matter, right? Because they match on name, not on order, but the order is the same. It just happens to work out that way, which is nice, okay? So we've got our test data set prepared for our final test, for our final exam. And then what we can do is encode the labels, because we need to do that too, right? Because we need the zeros and ones, because we can't work with the strings. Now here's what's really cool. We can reuse our label encoder object that we created earlier by build another one, right? Just use the one that we used before. So we say, hey, label encoder object, go ahead and just transform, don't fit, because we don't need to do that. We've already done that. So just transform the labels of the adult test data set. And I'm going to call this adult_test_y. And you can see here we get zeros and ones. So everything lines up, right? Everything lines up. The test X data frame has the same features, one-hot encoding, all that kind of stuff as the train X data frame. And similarly, the labels are all encoded the same way. So we're good to go. And then what we can do is we can start inspecting the model's predictions. Well, let me back up. So we do 2 things. 1, we ask the model to create predictions, and then 2, we inspect them to see how well the predictions perform, right? That's our final exam. So first thing that we can do here is we can ask the actual decision tree. Remember, this is my decision tree model, bad name. The object has a method called score, which is pretty handy. So we can say, hey, go ahead and score yourself against the test data set. So what this says is, hey, use these X's here, these predictors, and create predictions using the trained decision tree, which we've already seen the visualization of, right? So create predictions and then compare the predictions against the actual labels from the test data set. This is super important, right? So these are our answers from our student, if you will, right? The answers from the student or the machine learning model, and we compare them to the real answers, just like you would do on a final exam. And then this right here just says, look, just pull up, print out 4 decimal places only, please. Okay, so we can print that out. Now we can also create something called a confusion matrix. And a confusion matrix is best understood by looking at the output. So I'm not going to drain this code because you can Google it if you'd like, but in general, most of the time, all you're doing is you're copy and pasting this code, quite frankly, from Jupyter Notebook to Jupyter Notebook. That's what I do. And what's more important is actually looking at the confusion matrix visual and analyzing it and see what's going on. So let's do that. Okay. So if you run this code cell in the Jupyter Notebook, which I can send you, then this is the output that you'll see. So first up, you can see here that the decision tree made predictions on the test data set and then compared those predictions to the actual labels on the test data set. And what we find here is that the model is about 76% accurate, which is interesting. You might think that's a good score. You might think that's a bad score. A lot of it really depends on the nature of your problem, right? The more difficult your problem, the lower your scores are typically going to be. Your accuracy is going to be. Okay. This particular data set, this particular model isn't very good because it only used 4 features. If you include more features from the data frame, you actually can push the accuracy up, by the way, just so you know. And of course, you can get the code and play around with that and see it for yourself. Okay, but let's talk about what's going on with this confusion matrix. Okay, ignore this color band thing here. All this color band is telling you is like how many rows, right? How many rows of data? We don't really care about that. That's totally fine. What we're actually interested in is interpreting this. Now, what we can see here is the predicted label. So against the test data set, these were the actual labels that were predicted. Okay. Behind the scenes, it's zeros and ones, but we've mapped them to the original string values because that's what we want to do. Okay, cool. So the model predicted greater than 50K sometimes, and sometimes it predicted less than or equal to 50K. And then over here along the vertical are the actual labels, the true labels from the data. So for example, this particular quadrant, the true label, the actual label for the test data was greater than 50K, but the model got it wrong and predicted less than or equal to 50K. So when you look at a confusion matrix, the correct predictions go along the diagonal. And by the way, confusion matrices scale. So if you were predicting Olympic medals, bronze, silver, and gold, what you would get is a 3x3 matrix. And of course, the correct predictions would once again be along the diagonal here. And what this allows you to do is actually understand how well my model's doing vis-a-vis the actual labels. For example, you can see here that when the label is actually less than or equal to 50K, the prediction accuracy isn't very good, right? Because you can see here that we're right about 2/3 of the time. Because if we add these together, they're roughly 3,600. This is about 2/3 of 3,600. So we're right about 2/3 of the time. But over here, we can say, hey, when the actual label is greater than 50K, we have much better prediction accuracy, right? Because you can see here, we're right 3,165 out of approximately, what is that? 3,700-ish, which is not bad. So this model with just those 4 features and the hyperparameter values is better at predicting greater than 50K high income earners versus low income earners with an overall accuracy all up of around 76%. So this is super useful for understanding what's going on with your models. Okay. So you definitely want to use a confusion matrix. Phew, you made it. Made it all the way to the crash course. So if you're super excited about machine learning, if you like what you see and you want to learn more, let me give you some resources. Okay. So, and links to these books, by the way, I'll be in the description below. So first up, this right here is a free book. It's a great free book about various machine learning techniques. I know it says statistical learning, but tomato. it's you can think of it as machine learning. It's fine. It's a free book, PDF. There's also an accompanying website with some interesting materials here. This is a short book that covers a lot of different techniques. So it doesn't cover anything in any particular level of detail, just so you know. So this is like a survey book, essentially. Now, if you want to go more deep on decision trees and decision tree algorithms, which I would highly recommend because a lot of the stuff covered in this book, quite frankly, is more situationally useful. Generally speaking, decision trees are a great place for you to start and develop develop a lot of experience with them. Concentrate on like decision trees and other algorithms based on decision trees like random forests. It'll serve you well rather than trying to learn a bunch of different algorithms at a low level of detail. Learn a few at great levels of detail. It'll serve you well, and decision trees is a prime example of that. So if you follow my advice, you're going to be looking for a book, something like this. So this is the definitive work on the CART algorithm. This book is kind of hard to get. I had to wait for a while for Amazon to get it back in stock and send me a copy. You can see here on my dining room table along with this book here. And this book is exceedingly mathematical, by the way, just so you know. I mean, this is for not the faint of heart, right? It's like, it's the definitive work. So not surprisingly, it's a lot of effort to read it. But if you're so inclined, you can get this book. I wouldn't advise doing that for most professionals, by the way. What I would advise is this book. I love this book. This is the first edition copy. So when I learned machine learning in my master's in computer science degree program for the very first time, years and years ago, this is the book that we used. And it's a great book. There's more recent editions available on Amazon. This book is great. It's not Python specific. It talks about the algorithms and the techniques at a high level. No code in this book whatsoever. So it's great from that perspective because it really concentrates on the algorithms and the tools and the techniques. And it covers a lot of good stuff. It's got math, but it's not super mathematical. So it's it's very intelligible to a broad audience. You don't have to be a mathematician at all to read it. You don't need to be a computer scientist to read it. And it covers decision trees, random forests, clustering algorithms, all kinds of good stuff. So this is a great book. So it's a good thing to get. Generally speaking, if you're going to spend money, I would buy this book over this book any day of the week. So like I said, links will be down below in the description. Also, if you prefer a self-paced online course as opposed to a book, some people do, I've also got a link in the video description below to my online course, which introduces you to machine learning using decision trees and the random forests. It's a very complete course. It'll provide you with all the information that you need to actually do real-world machine learning. And there's also a promo code down there as well for 20% off in case that's the way you roll. Okay, there you go. So resources to continue your learning, choose your own adventure. That's it for this video. The next video in my data science crash course series is going to cover the mighty random forest algorithm, which is based on decision trees. So essentially it takes all the awesomeness of decision trees and then ratchets it up to 11. The random forest is a state-of-the-art production quality algorithm. So when that's ready, it'll show up here on the screen as a tile. And until next time, please stay healthy, and I wish you very happy data sleuthing.